Okay, class, we're starting on section 8.2, multiplying, dividing radicals. Now, objective 1, multiply square roots. We show that in this example that the square root of 4 times 25 is equal to the square root of 4 times the square root of 25. Now, you can only break the radical up like this when you're doing multiplication. So let's take a look at this. First, let's do the square root of 4 times 25. Now, we know 4 times 25 is 100. Now that's equal to the square root of 4 times the square root of 25 is also the square root of 100. So they are equivalent, which means 10 is equal to 10. So this statement is absolutely correct. Now, we come down here to the product rule for square roots. For non-negative numbers a and b, the square root of a times b is equal to square root of a times the square root of b. Now sometimes it's written with the multiplication sign in the middle, or it just may be square root of a square root b. It means the same thing. And the square root of a times the square root of b is equal to the square root of ab. Now, we scroll down here to example 1. It says use the product rule for square roots to find each product. We have the square root of 2 times the square root of 7. Neither one of these have a perfect square in it, so we will multiply it. So it would be square root of 2 times 7, all under the radical, which would be the square root of 14. Now you don't necessarily have to write this step here. You could just say square root of 2 times square root of 7 is the square root of 14. And they have no perfect squares in the square root of 14, so we're done with A. Now we come to B. Square root of 3x times the square root of 5x. Now, 3 times 5 is 15, and x times y is just xy. And there are no perfect squares here, so this is the finished product. Okay, now we come here to C. We have the square root of 5 times the square root of 5, which we know is the square root of 25. And the square root of 25 is just 5. Now we look here at D. We have the square root of x times the square root of x, which we know is the square root of x to the second power. Now the square root of x to the second power, that answer would just be x, because we know x times x gives us x squared. So that is it for D. Now we scroll down here to example 2. It says find the square of each radical expression. Now we have the square root of 7 in parentheses squared. So this is the same as the square root of 7 times the square root of 7. Now we know the square root of 7 times the square root of 7 is the square root of 49. And the square root of 49 is 7. Now we go here to B. We have the square root of 18 to the second power. Now, if you notice, the square is only on the 18, not the radical. So this would end up becoming the square root of 18 times 18. Now remember what you learned before. The square root just means what number times itself will give you the number under the radical. Since we have two 18s, isn't this a number times itself? So the square root of the value of 18 times 18 will give you 18. Now to clarify one thing, we did get 18, but just for clarity's sake, we know the square root of 18 times 18 is the square root of 324. And when you take the square root of 324, that gives you 18. Okay, now we come to C. We have in parentheses negative square root 5. And we have to multiply that by the negative square root 5. Because remember, this whole parenthesis is squared. So we know negative times negative is positive. And the square root of 5 times square root of 5 is square root of 25. And the square root of 25 is just 5. So your final answer here would be 5. Now we go to objective 2. A square root is simplified when the radicand does not have any perfect square factors. Simplify. Square root of 18. Now we know 18 is not a perfect square, but we do have perfect square factors in 18. Now, going back to section 8.1. Now going back to A1, objective 1, remember we did this table with the perfect squares. Now what you can do right now, you can pause it and then flip back in your course pack to get to this page. Now that you are at this page, if you come here, right here, we have the square root of 0 is 0 and so on. We have all of these values here. Now it says list all the integer perfect squares from 0 to 225. Now, if you look here, when n is 9, we have 3 and so on. Now what you need to do, not necessarily memorize these numbers, but you need to be aware of these numbers as far as do they go into the number that you see under the radical in the other lesson. Like for instance, what we were looking at was the square root of 18 previously. Now we have to ask ourselves, just based on the numbers that we have here, because we know with 18 we're not going to find a perfect square past 16, because that would be larger than what we have under 18. Now if you look at these numbers that are perfect squares, you got 0, 1, 4, and 9. We know 9 goes into 18. So for that previous problem, we would break 18 up to the square root of 9 times the square root of 2, because we know 9 times 2 is 18. Now the square root of 9 is 3, and we have our square root of 2. Now what I'm going to do is I'm going to go back to the problem and we're going to redo it so you will have it in that particular section. Now we just did the square root of 18. You know, you can pause it and get back to section 8.2 to come to this very problem that we left off on. Now the square root of 18, we know the highest perfect square in 18 is 9. So we'll break 18 up to the square root of 9 times the square root of 2. The square root of 9 is 3. And we bring down our square root of 2. So our final answer here is 3 times the square root of 2. Now this is what I like to do, and this is for your reference for later sections we do. I like to break these numbers up into 2 square roots. In the first square roots, I put all my perfect squares, and then in the last square root, I put all the numbers or variables that are not perfect squares. That's just something I choose to do. Now we go here to be the square root of 20. Now if you think for a little bit, if you look at the square root of 20, we have perfect squares 0, 1, then 4, then 9, then we have 16, and then we go to 25. Now we know of those squares that I just named, only 4 goes into 20 evenly. So we could break 20 up to the square root of 4, and then we will be left with the square root of 5. The square root of 4 is 2, and we bring down our square root of 5. Now we go down here to C. We add a square root of 50. Now we know the highest perfect square in 50 is 25. So in our other square root, we know we will have 2 left from the 50, and there's no perfect square in T, so we'll write the T here. The square root of 25 is 5, and we bring down our square root of 2T. And we're done. Now we go on to D. We have 3 times the square root of 28x. Now the highest perfect square in 28 is 4. So we'll bring down our 3, and we'll have our square root of 4. And then in our second parenthesis, we'll be left with 7x. And I didn't mean to say parenthesis, I meant radical. Okay, now we have 3 times the square root of 4 is 2. So it'd be 3 times 2, square root of 7x. 3 times 2 is 6 times the square root of 7x. So that is our final answer, 6 times the square root of 7x. Now we're given some directions here. It says, to simplify a square root in which it is difficult to determine the largest perfect square factor of the radicand, find the prime factorization of the radicand, look for pairs of identical factors of the radicand, and rearrange the factor to highlight them. Use the product property for square roots. Now listen, all this is saying is this here. Whenever you have a large number that you cannot automatically tell what the highest perfect square is in that number, they're suggesting that you use the prime factorization. And if any other numbers match up, you know, if it's 2, if it's an even number of them, then you know that you would need to pull out one of those. So I'm going to show you an example using A. Let's just say that we did not know what the highest perfect square was in 150. So we'll go over here and take 150 and do the prime factorization. We know we had 2 and 75. We will have 3 and 25. And then we will have 5 and 5. So now, our prime factorization would be 2 times 3 times 5 times 5. Now, if you look here, we could put that under the radical, and we will have 2 times 3 times 5 times 5. Now, when you use this method, this is how you would do it. Since we know the index of this square root is a 2, what this means is if you have 2 of the same, you only pull out 1 of them. Do we have 2 5s here? Yes, we do. So we'll pull out 1 5 in front of the radical. We don't have 2 of anything else, so what would be left under the radical is 2 times 3. Now let's take a look at that again. We take the prime factorization. We group this because this index is 2. We group them by 2's. Since we have 2 5s, that means that we could pull 1 5 out, which we did here. And then anything that we cannot have two or more of, we have to leave under the radical, which we have here. So now, what's 2 times 3? And we know that to be 6. So this will be our final answer, 5 times the square root of 6. Now let's go over here to 360. I'm going to write this here, the prime factorization of 360. You have 2 times 180, and then 2 times 90, 2 times 45, 5 times 9, and finally 3 times 3. Now what I always like for you all to do when we did prime factorization is write these in order from smallest to greatest. And I'll write this down at the bottom. We will have 1, 2, 3 2's, 2 3's, and a 5. Now we'll put this under the square root. Now we'll have our 3 2's. We have our 2 3's. And we'll also have our 5. Okay, now remember, we group them. We have 2 2's here, so we know we'll pull 1 2 out. We have 2 3's here, so that means we'll pull 1 3 out. Now, after we pull these out, we're left with a 2 and 5 under the radical. So we leave our 2 times 5 under the radical. Now, we would take 2 times 3, which is 6. The square root of 2 times 5 is 10. So our final answer here is 6 times the square root of 10. Now again, you always set them up in groups of 2's when you're dealing with a square root. 2 sets of 2's, we pull out 1. 2 sets of 3's, we pull out 1. And what's left is this 2 and 5. So then we will end up with 6 times the square root of 10. And we're done with that problem. Okay, now we come to example 5. It asks us to simplify. Now we know 19 is actually a prime number, but we know x squared is a perfect square. So we could break that up. We will have the square root of x squared times the square root of 19. The square root of x squared is x, and we bring down our square root of 19, and that is our final answer. Now we come here to b. The highest perfect square we know in 8 is 4, and x squared is a perfect square, so we'll put it under that radical. Under the second radical, we'll just be left with 2. The square root of 4 is 2. Square root of x squared is x, and we bring down our square root of 2. So we'll have 2x times the square root of 2. Now we come down here to 45, a to the 6. The highest perfect square in 45 is 9. A to the 6 is a perfect square, and we'll be left with 5 under the second radical. Square root of 9 is 3. Square root of a to the 6 is a to the third, and we bring down our square root of 5. And that is the final answer for that problem. Now we come here to D. Now D is where we're going to start because 75 is a larger number. We'll start using the prime factor